So we have discussed Faraday's law. Let's try to apply Faraday's law in this question over here. So it says that if the magnetic flux through a coil of 60 turns change at a rate of 0.038 Weber per second, calculate the induced EMF in the coil. Okay, so they say that you have a coil. Sorry. They say that you have a coil and this coil has 60 turns. Okay, and because this coil here is in a magnetic field, okay, I'm going to draw a very rough magnetic field. Because this coil here is in a magnetic field, therefore this coil will have a magnetic flux. And from the question, they say that the magnetic flux is going to change at a rate of 0.038 Weber per second. It's magnetic flux changing rate. It's not magnetic flux linkage changing rate. So in this case, this is d phi over dt. And this should be a small phi, not a big phi. Okay? Because big phi will be magnetic flux linkage. Small phi will be magnetic flux. Okay? So you know all this already. They ask you to calculate induced EMF in the coil. So epsilon is equals to negative d. Here you have multiple terms, so it's d big phi over dt. So the time rate of change of the magnetic flux linkage, and you know that it is equals to negative nd small phi over dt. So we have all the value we need. Negative 60 d phi dt is 0.038. Then I believe you should be able to get the answer, which is 2.28. And this is EMF, therefore the voltage is equivalent to voltage in terms of its unit. So it's 2.28 volt. Okay, that's negative. Okay, you don't throw the negative simply. So okay, before that, I mentioned that the sign over here will allow us to determine the direction of the induced EMF and the direction of the induced current. Okay, but in this situation here, the sign will be useless. Technically, what you are doing is you are calculating the magnitude of the induced EMF only. You cannot determine the direction of the induced EMF. Why? Because in this question over here, they just say the magnetic flux is changing. But changing doesn't tell you whether it's increasing. It doesn't tell you whether it's increasing or it's decreasing. That is actually very important information for us actually. If it's increasing, right, then this d phi dt here is a positive d phi dt. If it's decreasing, then it's a negative d phi dt. So we don't know whether it's increasing or decreasing. So we don't know whether this value over here, we are not sure whether it should be positive or negative. Okay, because we don't know whether it's increasing at the rate of 0.038 Weber per second or decreasing with a rate of 0.038 Weber per second. So since we don't know this value 0.038 should be positive or negative, so that means by our answer, right, there's a possibility that it's a positive answer, there's a possibility that it's a negative answer. What you're getting here is just the magnitude only. Because if you substitute because if you substitute positive here, then you get a negative answer. So that means by if your magnetic flux is increasing at a rate of 0.038 Weber per second, then your induced EMF will be negative 2.28 volt. But if your magnetic flux is reducing or decreasing at a rate of 0.038 Weber per second, then you need to put negative here. If it's decreasing, then you become positive 2.28 volt for your induced EMF. Then at that point only we can talk about the direction of the induced EMF based on the sign of our answer of our induced EMF. But for now, the sign over here, even though it's negative, it doesn't carry much meaning because we are not even sure whether we will be a positive 0.038 or negative 0.038. We don't know the sign, therefore we cannot know. Therefore, the answer for induced EMF, what sign it does not carry a direction anymore because you don't know the increase or decrease. Okay, so this is example 17.10.